All right, welcome to Next Gen Manufacturing. Today, we're going to shrink things way, way down to explore the ultra-precise world of micromachining. This isn't just some cool niche. It's literally the foundation for so much next-generation tech. So let's dive in and get a handle on it.
So, here's what we've got on tap. First, we'll get our heads around what micromachining even is. Then, we'll get into why it's so tricky, or the normal rules just seem to break down. After that, we'll look at the smart ways to program a perfect toolpath, pull it all together into a pro's checklist, and finally, we'll talk about why this tiny stuff is such a huge deal for the future. Okay, let's jump right into section 1. First things first, let's talk about scale. Just how small are we talking here, and what really defines this incredible technology? So, what exactly is micromachining? Well, it's when you're working with end mills under 1/8 of an inch in diameter. We're talking about tools that can literally be finer than a human hair. And here's the thing, in the world of machining, size is strength. So when your tool is this small, it's just incredibly fragile. It means that every single variable, the machine, the material, even the temperature in the room, has to be locked down with absolute, unbelievable precision. All right, now this is where things get really, really interesting. Because when you get down to this tiny scale, the familiar rules of machining, well, they start to bend. In fact, sometimes they just completely break. The physics are just different. Okay, take runout. That's just a tiny wobble in the tool. In conventional machining, a little runout is no big deal. It might cause some extra wear, you fix it later. But in micromachining, that same tiny wobble is an absolute catastrophe. It's not a maintenance issue, it's an instant tool snapping, part-ruining disaster. Game over. And here's the number you have to live by, 2%. The maximum allowable runout is just 2% of the tool's diameter. Now that might not sound like a lot, but for a tool that's already microscopic, 2% is, well, it's practically nothing. We are talking about tolerances measured in single microns. Go over that, and you're not cutting parts, you're just making a pile of broken tools. And it gets weirder. There's this phenomenon called the size effect, and it's a real mind bender. Think about it like this. A really sharp axe shears right through a piece of wood, right? But what if you try to split that wood with the back of the axe? It just mashes and pushes it. That's kind of what happens here. At the microscale, the tool's cutting edge, even if it's perfectly sharp, is actually thicker than the tiny chip you're trying to cut. So instead of shearing off a clean chip, the tool just plows through the material. So here's what that plowing effect looks like up close. The tool comes in, but instead of cutting, it just squeezes and pushes the material down. Then, once the tool passes, the material springs back up. All that squeezing and rubbing creates a ton of friction and a crazy amount of heat. You end up with a ruined tool, sure, but also a terrible surface finish, and that's a huge deal. Imagine this is a medical implant. A rough surface like that, it could cause a patient's body to literally reject it. That's the kind of high-stakes problem we're solving here. Now check out this quote. This one always gets me. Doubling the length sticking out of the holder will result in 8 times more deflection. Just let that sink in for a second. 8 times. It's not a linear problem, it's exponential. That's why keeping these tools as short and stubby as possible isn't just a best practice, it is the only way to do this. The tiniest bit of bend and that tool is gone. And hey, it's not just about the tool. The challenges keep coming. At this scale, the material you're cutting, the workpiece, becomes a minefield. What looks like a perfectly smooth, solid block of metal to you and me, to a micro tool, it's a lumpy landscape of different crystal grains and impurities that it has to bash its way through. And to top it all off, because of that plowing effect we talked about, you're way more likely to get burrs, those nasty little slivers of metal that can completely ruin a high-precision part. Okay, so we've laid out all the problems, right? It sounds kind of impossible, but it's not. So let's talk solutions. It all starts with programming the perfect toolpath. One that treats these fragile little tools with the respect they deserve. The number one rule, you have to treat the tool like it's made of eggshells. You would never just slam it straight down into the material. No way. Instead, you have to ease into the cut. Use a gentle ramp, or you arc in from the side. The whole idea is to gradually introduce the cutting forces, to avoid that sudden impact that will snap the tool in a heartbeat. Now, here's a detail that's super easy to miss, but it's absolutely critical. When your tool is machining in a circle, think about it. The outside edge of the tool is traveling a longer distance than the inside edge in the same amount of time. That means it's moving much, much faster through the material. If you don't adjust your feed rate to compensate for that, what's called compounded angular velocity, you're going to generate way too much heat and just fry your tool. And this is where you have to flip your brain upside down. because the strategy for slotting is a complete reversal of conventional machining. Normally, you'd think deep, slow cuts, right? Nope. For micromachining, you do the exact opposite. You take these incredibly light, shallow passes, we're talking just 5 to 15% of the tool's diameter, but you crank up the feed rate to keep things moving. The mantra is light and fast, light and fast.
Here's a great pro tip. It's just simple physics, really. When the tool goes around a corner, more of its cutting edge engages with the material all at once. That causes a sudden spike in cutting forces. It's exactly like driving a car. You don't take a sharp turn at full speed, right? You slow down. You have to program your tool to do the same thing, to ease around those corners so it can handle the extra load without snapping.
All right, we have covered a ton of ground. We've seen the problems, we've seen the strategies. So now let's pull it all together into a pros checklist, the key takeaways you need for success.
And here it is. This is the ultimate playbook. It all starts with a setup. Minimize that runout and deflection with good holders and keeping the tool short. Then it's about the physics. Pick a depth of cut that actually cuts instead of plows. From there, it's about strategy, using coated tools to handle heat, maybe even using support materials to prevent burrs, flooding it with coolant to keep things stable, and always, always scrutinizing your tool path to make sure you're applying force gradually. Every single item on this list is non-negotiable.
Okay, so let's zoom out. We've been deep in the weeds with all these tiny, tiny details. So, why does this all matter? Why are we so obsessed with this? Because this micro-sized world is building our macro-sized future. Here's the bottom line. Mastering the microscale isn't some niche specialty anymore. It's not optional. It is the absolute foundation for the next wave of innovation in medicine, in electronics, in aerospace, you name it. The next generation of medical implants that save lives, the tiny chips that power our world, the complex parts that take us to the stars, they all depend on getting this right. This is a core competency of next-gen manufacturing. So that really just leaves us with one final thought to chew on. We've talked about what's being built now, but what comes next? What future technology will be built on these tiny foundations? It really is an exciting time. Thanks for joining me for this deep dive into the incredible world of micromachining.